Hello and good morning, dear students. Now we are moving to last lecture of your chapter number 5 and last lecture of your course classical mechanics. So here in this lecture, first of all, we are going to see last topic, which is proof of Jacobi identity. So Jacobi identity, as I told you, we can write for three variables, dynamical variables u, v and w, and that is cyclic relation. So cyclic relation can be written as, say, commutator u, okay, Poisson's bracket u and Poisson's bracket vw. So this is implicit type of Poisson's bracket, plus second one is v and wu, okay, plus w and uv, okay, Poisson's bracket, and this is equal to 0. So uvw. Now to prove this Jacobi identity, we have to start with this from definition. So from definition, vw is, we know that summation over k partial derivative of v with respect to q, okay, partial derivative of w with respect to p minus partial derivative of v with respect to p and partial derivative of w with respect to q. Now next, with this definition, you can write u v w is equal to u, okay, and this term can be written as summation over k partial derivative of v with respect to qk, okay, partial derivative of w with respect to pk minus next term is partial derivative of v with respect to pk and partial derivative of w with respect to qk. So next you can write this is equal to, so u, again using definition of Poisson's bracket, if you called all this term as x, so you can write partial derivative summation over k partial derivative of u with respect to qk and partial derivative of this term with respect to pk minus next is partial derivative of u with respect to pk and partial derivative of this term with respect to qk. So if in the next step, if you do calculations like partial derivative with respect to pk of all these terms, so we are taking derivative of this term with respect to pk. So here you will have two terms. First one is derivative with respect to pk of this term, okay, at that time this term is constant, plus this term is constant derivative of this term. So you will have four terms, two for this term, two for this term corresponding to this. So 4 multiplied by this, again you will have four terms for this, okay. So you will have total of 8 terms. Now similarly you can take second term vwu over here. So you will first take wu and then again commute Poisson's bracket of this, simply writing down it like this, you will again have 4 plus 4 terms. Here you will also have 4 plus 4 terms. So combine all those terms, so 8 8 8, you will have 24 terms. So all the 24 terms that you can write, and those terms are negative of one another. So for each and every term you will have negative term. So by solving this, I will keep you this as an exercise. You will end up with that is equal to 0. Now we are moving to problems. So here I already written two problems. So we are going to solve those two problems on chapter number 5. First problem is solution of first problem. So first problem is f and g are functions of q and p. Then show that first one, Poisson's bracket of f and ql is minus partial derivative of f with respect to pl. Second, Poisson's bracket of qk and ql is 0. I think we already shown this. Poisson's bracket of pk and ql is minus Kronecker delta kl. This is, I think, we already shown in the previous lecture. So we, and third identity, commutator, Poisson's bracket of f and pl is partial derivative of pf with respect to ql. So that we have to prove. So we start with definition. Okay, Poisson's bracket of f and g is, we know that, summation over k partial derivative of f, which is first function, with respect to qk, partial derivative of g, which is second function, with respect to pk, minus second term is partial derivative of f with respect to pk and partial derivative of g with respect to qk. Okay, so here if you put g, which is second term, as ql in above equation, so you will get Poisson's bracket of f, and instead of g we will have ql is equal to summation over k. Okay, first of all, partial derivative of f with respect to qk. So f with respect to qk and partial derivative of g, now g is what, ql with respect to pk, minus partial derivative of f with respect to pk into partial derivative of g, now g is what, ql, so ql with respect to qk. So this is equal to, now here we are taking derivative of q with respect to p, so this term is 0. So we have second term, so minus summation over k partial derivative of f with respect to pk, and here instead of this we can write as Kronecker delta kl, because here we are taking derivative of ql with respect to qk. So here if you put k is equal to L in this equation, you already know properties of Kronecker delta function, as I told you early lecture, previous lecture. For k is equal to L, this is equal to 1, and for k is not equal to L, this is equal to 0. So if you put k equal to L over here, then you will get commuted Poisson's bracket of f and ql as minus, on the right hand side, if you put k is equal to L, partial derivative of f with respect to pl. Okay, and that is right hand side. Now to prove second identity, if you put, call this as equation 1, put f is equal to qk in equation 1, you will get, so instead of f, if you put qk, so Poisson's bracket of qk, ql is minus partial derivative of f. Now f is what, qk, so partial derivative of qk with respect to pl. So again we are differentiating q with respect to p, so derivative of q with respect to p is 0. Okay, and that is right hand side of identity number 6. So identity number 4, to prove identity number 4, we prove this identity later. Okay, so if you put f is equal to pk in equation 1, in this equation, so what you will get, Poisson's bracket of f, you have, instead of f we can write pk, ql is equal to minus partial derivative of f, which is pk with respect to pl, and that is nothing but Kronecker delta kl. Now we are proving identity number 3. So in third identity we know that from definition of Poisson's bracket fg is this, if you put g is equal to pl here, then Poisson's bracket of f and pl is equal to PL. Here you will have PL. So this is nothing but now this term is not equal to 0. Okay. Now this term is 0. Why? Because derivative of P with respect to Q is 0. So here you will have partial derivative of F with respect to QK, and instead of this term partial derivative of PL with respect to PK, we can write commutator delta KL. So again, if you put K equal to L, so we can write commutator Poisson's bracket FPL is equal to minus partial derivative of F with respect to QL. Okay, and that is right hand side. With this we finish first problem. Now we are moving to problem number 2. What is problem number 2? So problem number 2 is prove that if u and v are constants of motion, then Poisson's bracket of u and v is also constant of motion. Okay, that we have to prove. Since u and v are constants of motion, so since solution of second, since u and v are constants of motion, we know that commutator of u and Hamiltonian is 0 and commutator of u, v and Hamiltonian is 0. So this is definition of constant of motion. If you take commutator with respect to Hamiltonian, so that becomes 0. Now from Jacobi identity, what is Jacobi identity? Poisson's bracket of u, v, w. Okay, then Poisson's bracket of v, w, u, and Poisson's bracket of w, u, v. This is equal to 0. Okay. Now here in this Poisson's bracket, if you put w is equal to h, which is Hamiltonian, okay, then this becomes u, okay, v and h, okay, plus v and h and u, okay, plus here we can write h and uv. So this is equal to 0. Now since u and v are constants of motion, we know that Poisson's bracket of h and v is also 0 and Poisson's bracket of h and u is 0. So these Poisson's brackets are 0. So we end up with only last term. So what is last term? Poisson's bracket of h and uv is 0. So using equation 1, so this is equation 1, we get this. And from definition of Poisson's bracket, since Poisson's bracket of h and uv is equal to 0, we can say Poisson's bracket of uv is constant of motion. Okay. Now with this, our syllabus of classical mechanics is over. So I think all the best for your examination. Do well in exam. And if you have any query or question, you can contact me directly.